Good to go? Okay. Excellent. So it's exam time again, and this is the mock exam, and you will have noticed when you sat it that it was last year's paper. Ha ha! Unadulterated. So this is component 2, and this is question 1 from last year's paper, and this is the one that caused an absolute furore on Student Room and Twitter, and yes, your teachers are in the student room, beware. So, because students went, do they not know what's on their own components? Well, yeah, the bottom line is they probably do know what's on their own components, but how many times do I have to tell you? Synoptic. So there's a bit of core on this and a bit of component 3. So, we're talking about lysosomal storage disorders, about 50 diseases characterised by an accumulation of waste products in the lysosomes. So that's your big key in there, that we're actually going to be doing a bit of core here. 2 examples are Fabry disease and Tay-Sachs. Sufferers of Tay-Sachs disease die in childhood. Tragic. The electron micrograph above shows the cell organelle responsible for producing lysosomes. Name the organelle. Let's do that straight away. Producing lysosomes, so Golgi body or apparatus, whatever you decide. Name the organelle, draw an arrow labelled L on the micrograph to identify a lysosome, and describe a general function of lysosomes. So this is the Golgi body, these curved stacks of cisternae, just in case you hadn't remembered. So all of these sort of vesicles up here on this end will be lysosomes. So I'm just going to pick the biggest one and stick a label right to it. And it says I've got to label it L, and I've got to draw an arrow, so I'm going to put an arrowhead on it for once. Okay. Describe a general function of lysosomes. So I'm just going to make sure that the examiner knows that I'm talking about lysosomes now. And these contain hydrolytic enzymes, and why wouldn't you call them that? I was just about to say because I can't spell it, but anyway. Hydrolytic enzymes, to break down worn out organelles. I know they do other stuff as well. So you could have probably referred to phagocytic vesicles, macromolecules. You might have had them transporting enzymes around the cell. But if we look at the 3 marks, one for the label, one for Golgi body, one for telling me the function of lysosomes, easy peasy. So B, the symptoms of Tay-Sachs disease are a consequence of abnormal accumulation of fatty substances in neurons. And as soon as I see that, I'm thinking myelin sheath. And presumably you did too. Complete the diagram of a neuron below to show how this fatty substance is usually distributed. Your labels should include the name of the fatty substance. So it's kind of usually distributed, kind of like that. With gaps in between. I'm going to put some labels on. I'm going to put 2 on actually, just in case. So I'm going to label that. Myelin sheath. And I'm going to label that node of Ranvier. So actually the mark scheme just says myelin sheath drawn with nodes, myelin correctly labelled. So I could have got away without labelling a node as long as it was present. So this is component 3, isn't it? So that's another bit of synoptic there. So we've got synoptic core, synoptic component 3, and moving on, it says explain how the arrangement of the fatty substance affects the transmission of nerve impulses. And again, synoptic, but it's, you know, this is absolute baseline knowledge, isn't it? Really. So, what are we going to say? It speeds up transmission, and I know I say don't write it, but it's the arrangement of the fatty substance, so I think we'll be okay using it on this occasion. Speeds up transmission by lengthening local currents. This is basic AO1 stuff from component 3. As ions can't move except at nodes. And then we put action potentials, jump, and we put that in inverted commas. It's how we usually express it, but it's not really a jump, is it? No legs. From node to node, which is, and I would always put this in a fatty sheath bit, saltatory conduction, because sometimes that's just worth a mark, all on its little own. So there we go. The diagrams below show gene maps of human sex chromosomes and chromosome 15. The recessive allele that causes Fabry disease is carried on the X chromosome. The recessive allele that causes Tay-Sachs is at the locus labelled little h. So that's where the Tay-Sachs one is. Mark by placing the letter F a possible locus for a gene that causes Fabry disease. So, what do they tell us about Fabry disease? It's carried on the X chromosome, so it can't be anywhere where it could be homologous with a Y chromosome. So anywhere outside of those, I would guess. So I'm going to do a label line again. There's a lot of labelling on this. So I want to label it. Oh, I'm going to pretend it's there. I don't know. I mean, you're not supposed to know. You just need to, so what they're testing here is really, do you know the difference between an X and a Y chromosome and sex linkage and not sex linkage? So we're back in component 2 now. With reference to the positions of the gene loci, explain the following observations. Males with the F allele always suffer Fabry disease, but females can have the F allele without. So, so again, standard answer, isn't it? Females have 2 X chromosomes and can be heterozygous. And males have only 1. I think that'll probably be 2. I'll just I'll put in a genotype there, just to make sure that they know what I'm talking about. I know what I'm talking about. So, males and females can have the H allele. So this is the one that's not on a sex chromosome. This is on an autosome. Males and females can have the H allele without suffering Tay-Sachs. They can be heterozygotes h, little h. I'm just going to further explain that, because they both have a homologous pair of, I don't know, I can fit this in, chromosome 15. Okay, turning over. Complete the genetic diagram to show how Fabry disease, so this is the sex-linked one, isn't it? Yeah. So let's just, sex-linked. Might be inherited from parents neither of whom suffers from the condition. So that means that the female has got X big F, X something, and she's going to be crossed with, he hasn't got it, so he's got X big FY, and state the probability of this couple producing a child. So actually, if you're saying how it might be inherited, then the female's got to be X little f. So parental phenotype is non-sufferer, and she is a non-sufferer. Parental genotypes: male X big F Y, female X big F X little f. Gametes. Now I like to put my gametes in circles, and then it's really clear that they're gametes. Do not just write them in a line like that without separating them in some way. You can separate them with a comma, that's absolutely fine, but it must be really obvious it's the gamete and not just the genotype. And I'm going to shove that into a Punnett square. X big F Y, X big F X little f. So we've got female, not sufferer, male, not sufferer, female carrier, male sufferer. Probability of this couple producing a child with Fabry disease, you can put 1/4, or you can convert it into percentages. Probability or percentage, any of those will do. So, the genetic counsellor advised a woman with Fabry disease in her family to have an amniotic fluid test 10 weeks into her pregnancy in order to determine the sex of the embryo, because obviously there's a 50-50 chance if it's a boy. Explain the function of amniotic fluid. So this is to cushion the fetus and protect it from mechanical shock. If you fall over, the fetus will be all right. Why might it be important for the woman with Fabry disease and her family to know the sex of the embryo? What ethical issues might this cause? So 50% of the male offspring may be sufferers. Obviously really that's a probability rather than a, if you've got two boys, half of them, one of them will have it. Females won't. Oh, it's all very noisy in there today. And the ethical issue is whether to terminate the pregnancy. Because obviously there's a 50% chance that the male may have it, but there's 50% chance that they won't. Okay, excellent. Oh, the Hardy-Weinberg principle. Brilliant. States that the frequency of alleles for a given gene remains constant from generation to generation, providing the population is large and no selection takes place. Frequency of Tay-Sachs, so this is the non-sex linked one, isn't it? So we can use Hardy-Weinberg. So this is autosomal. Is 1 in 3,600 births. So that is going to be our Q squared. However, frequency is 1 out of 40,000 in certain populations which isolate themselves culturally. So that means they're only marrying within their own communities. One such population is the old order Amish of the, I can't even pronounce that, Kishakakila, Pennsylvania. Recent estimates put the size of this population, so that's the overall population size, at 40,000. Using the Hardy-Weinberg equations, calculate the number of people in the Amish community that carry, so this is the heterozygotes. So that's 2pq, the Tay-Sachs allele. So, let's work out Q first. So Q squared is 1 over 40,000. I want the square root of that, and I've got this really rubbish calculator. 1 divided by 40 into 3. I want the square root of that. So Q equals 0.005. So, because P plus Q equals 1, P equals 1 minus 0.005, which equals 0.995, and we want 2pq. So times 0.005 times 2 is 0.00995. And then we want it, how many of them? So we need to times by 40,000. I'm just going to check that calculation again. So population, the frequency, 1 divided by 40,000 equals square root, that's right, minus plus 1, that's right, times 2 times 0.005 times 40,000. 398. Job's a good one. So, explain why the frequency of Tay-Sachs is higher in isolated populations and predict with a reason what is likely to happen to the frequency of the Tay-Sachs allele in the general population. So, isolated populations, you can talk about isolated populations are not mating randomly with the bigger population. Population. Still lots of hilarity going on in the office. And the populations are small and subject to genetic drift. So I've given two reasons there. I would normally say, oh, don't bother. But I don't know what the examiner's quite got in mind here. So I want to say something about each of these. You might even get away with just saying, I can't spell drift. You might even get away with just saying, there's no immigration and emigration because they're isolated. So that's part one. What's likely to happen to the frequency in the general population? Right, I'm sure they said something about dying earlier on. Sufferers of Tay-Sachs disease die in childhood. So the allele frequency, I've read something at the beginning. In the general population, should decrease as sufferers die before reproducing. You've got a net loss then of alleles. So the alleles, I want to stick a term in here, are lost from the gene pool. Gosh, that felt like the longest question in the universe. Can't remember how you switch this off now. Excellent.